Column Matrix Introduction. Hello everyone. Today we are beginning our lesson on column matrices. To start, it is important to understand that in the study of linear algebra, matrices are not all the same. They are classified into various types based on their dimensions, which we refer to as the order and the specific arrangement of their elements. Among these different types, one of the most fundamental and simplest forms is the column matrix. Now, how do we identify one? A matrix is classified as a column matrix if it consists of exactly one column. To clarify, the number of rows does not matter. Regardless of whether there are 2 rows or 20, as long as there is only one vertical line of elements, it is a column matrix. In the following slides, we will dive deeper into the mathematical structure of these matrices and look at how they are used to organize real-world data. Understanding the structure. Now that we have established the basic definition of a column matrix, let us dive deeper and break down its structural components to understand how it is formally defined. First, let's discuss the order of the matrix. In linear algebra, the order of any matrix is always written as the number of rows multiplied by the number of columns. Since a column matrix, by definition, consists of exactly one column, if it contains m, number of rows, its order is expressed as m by 1. Next, let's look at the general mathematical notation. A column matrix, which we will call A, is represented as a bracket containing a sub ij with a subscript of m by 1. To clarify these terms, A is simply the name of the matrix. The symbol a sub ij represents the specific element located at the ith row and the jth column. A crucial point to remember here is that in a column matrix, the column index, j, is always equal to 1. The letter m represents the total number of rows present in the matrix. Finally, let's consider the visual representation. A column matrix appears as a vertical stack of numbers. If we were to write this out, matrix A would show elements a sub 1, 1, a sub 2, 1, and continuing down to a sub m1. Notice how the second index remains 1 throughout, while the first index changes to indicate which row the element belongs to. Understanding this formal structure is essential, as it provides the blueprint for how we organize data vertically, which we will see in our real-world example in the next slide. Real-world example, student grade tracking. Now that we have discussed the theoretical definition and the general notation of column matrices, let us apply this knowledge to a practical, real-world scenario to see how it works in practice. Imagine a teacher who wants to record the marks of a single student across 3 different subjects: mathematics, physics, and chemistry. Instead of writing a descriptive sentence, the teacher can represent this data more efficiently using a column matrix. Let us walk through this process in 3 simple steps. Step 1 is to identify the data. In this case, the student has scored 95 in mathematics, 88 in physics, and 92 in chemistry. Step 2 is to determine the order of the matrix. As we learned in the previous slide, the order is defined by the number of rows and columns. Here, we have 3 subjects, which will serve as our 3 rows, and since we are recording data for only one student, we have exactly one column. Therefore, the order of the matrix will be 3 by 1. Finally, in step 3, we construct the matrix. We place the marks vertically in a single column. We will name this matrix M inside the matrix brackets. We list the values 95, 88, and 92 stacked one on top of the other. In this example, M is a column matrix of order 3 by 1. By organizing the data this way, we have a clear, vertical representation that fits the exact definition of a column matrix. In the next slide, we will summarize the key takeaways to ensure you have a firm grasp of these concepts. Key takeaways. Now that we have seen how a column matrix works through the student grade example, let us summarize the key takeaways to ensure you have a solid grasp of the concept before we move on. First, let's revisit the definition. Simply put, any matrix that consists of only one single column is classified as a column matrix. Next, let's talk about the order. As we discussed in the structure section, we always state the number of rows first and the columns second. Therefore, the order of a column matrix is always expressed as m cross 1, where m represents the total number of rows. In terms of mathematical notation, we denote this as capital A equals a sub ij, with the subscript m cross 1. This notation is just a formal way of saying that the matrix A contains elements where the column index is always 1, regardless of how many rows there are. Finally, regarding its visual shape, you can identify a column matrix by its appearance. It looks like a vertical vector or a single column of entries stacked on top of one another. Please keep these 4 points in mind, as they will help you avoid some of the common pitfalls we are about to discuss in the next slide. Common mistakes to avoid. First, let's address the confusion between rows and columns. It is quite common for beginners to mistake a row matrix, which consists of one row and multiple columns, for a column matrix. To keep this simple, always remember that a column is vertical. A helpful tip is to look at the shape. If the matrix stands tall, it is a column matrix. Next, be very careful with the order notation. You must not write the order as 1 by m as we discussed in the second slide. The first number in the order always represents the number of rows, and the second number always represents the number of columns. Therefore, for any column matrix, the second number in the order must always be 1. Finally, let's talk about misidentifying the index of the elements. In a column matrix, since there is only one column, the column index represented by the letter J is always equal to 1. Consequently, the elements will always follow a specific pattern. They will be written as a sub 1 1, a sub 2 1, a sub 3 1, and so on, continuing down to a sub m1. Now that we have covered the definition, the structure, and a practical example of column matrices, let us conclude by discussing some common pitfalls. It is important to be aware of these mistakes to ensure your calculations and notations are accurate. By keeping these 3 points in mind, you will be able to identify and construct column matrices with confidence.